Welcome. Get ready to see linear algebra in a completely new way. Let us start from the very beginning. What exactly is a matrix? A matrix is simply a rectangular array of numbers organized in rows and columns. But here is the key insight. A matrix represents a linear transformation. It is a function that takes vectors as input and produces vectors as output. Let's visualize what a matrix does to space. Imagine we have a 2D grid representing our space. Watch what happens when we apply a matrix transformation. The matrix stretches, rotates, and shears the space. Understanding where vectors can go and which vectors go to zero is what the four subspaces are all. Let's start with the simplest possible matrix. This is a diagonal matrix where the diagonal entries are 2 and 1. This matrix stretches the x direction by 2 and keeps the y direction the same. Now for the column space, the first and most important subspace. The column space answers this fundamental question. Another way to think about it: what are all possible outputs of the transformation? Mathematically, we write this as a times x for all possible x. Let's see the columns of our matrix. Here's our matrix again. Column 1 is the vector that results from multiplying a by 1, 0. Column 2 comes from multiplying a by 0, 1. So the column space is all combinations of these two column vectors. Now let's visualize the column space geometrically. Here's our 2D coordinate system. Column 1 is the vector 2, 0, pointing along the x-axis. Column 2 is the vector 0, 1, pointing along the y-axis. Let's create some combinations. For example, 2 times column 1 plus 3 times column 2. Here's another combination. 1 times column 1 plus 2 times column 2. And one more, 3 times column 1 plus 1 times column 2. Since these two columns point in independent directions, we can reach any point in the plane. Therefore, the column space is all of 2D space. Let's pause and understand what dimension means. The dimension is the number of independent directions in a space. A line has dimension 1, you can only move in one direction. A plane has dimension 2, you can move in two independent directions. For our matrix, both columns are independent, so the column space has dimension 2. Now for the null space, a completely different kind of question. The null space asks, what gets destroyed by the transformation? These are vectors that disappear, they get mapped to the origin. Mathematically, we solve Ax equals the 0 vector. Let's understand this geometrically first. Imagine our matrix is squashing space. For most vectors, they just get transformed to a new location. But vectors in the null space collapse to 0. For our specific matrix, let's find what goes to 0. Let's solve for the null space step by step. We need to solve Ax equals 0. Multiplying this out gives us two equations. From the first equation, 2x equals 0, so x must be 0. From the second equation, y equals 0. So the only solution is the 0 vector. This means the null space contains only the 0 vector. Let's visualize this null space. Here's our coordinate plane. The null space is just this single point at the origin. Let's verify. Pick any non-zero vector and see it doesn't go to 0. When we multiply by a, we get 2, 2, which is not 0. This is actually a good thing. It means our matrix doesn't lose any information. Now for the third space, the row space. The row space is like the column space, but we use rows instead of columns. Let's see our matrix with rows highlighted. Row 1 is 2, 0. Row 2 is 0, 1. The row space consists of all linear combinations of these row vectors. Here's an important observation about row space and column space. For our matrix, the column space and row space are actually the same. They're the same because our matrix is symmetric and full rank. More importantly, their dimensions are always equal. This is the rank. Finally, the fourth and last space, the left null space. This is the trickiest one to understand, so let's go slowly. Remember the regular null space? It's vectors x where ax equals 0. The left null space is vectors y where y transpose times a equals 0. It is called left null space because y is multiplying a from the left. Equivalently, it's the null space of A transpose. Now let's see the big picture, how all four spaces fit together. On the left, we have the input space, which is R squared. On the right, we have the output space, also R squared. The matrix A transforms the row space into the column space, and the null space gets completely collapsed to 0. These four spaces tell us everything about what the matrix does. Let's see a more interesting example, a projection matrix. This matrix projects every vector onto the x-axis. Let's visualize what this does. Take this vector, 2, 2. After projection, it becomes 2, 0. It's been squashed onto the x-axis. Now here's the key. What is the column space? And what is the null space? Any vector on the y-axis gets sent to 0. Notice they're perpendicular. This is always true. Here's another example, a rotation matrix. This matrix rotates vectors by 45 degrees. Watch how it rotates vectors. Here's a vector pointing right. After rotation, it points at 45 degrees. For a rotation matrix, nothing goes to 0, the null space is empty. And every vector in R squared can be reached. The column space is all of R squared. This is what we call an invertible or full rank matrix. Now for one of the most beautiful facts in linear algebra. The four subspaces come in two perpendicular pairs. First pair, row space is perpendicular to null space. Second pair, column space is perpendicular to left null space. Let's visualize what perpendicular means. Let's summarize all the dimension relationships. For an m by n matrix, here are the key facts. These relationships hold for every matrix, they're fundamental laws of linear algebra. Why should you care about these four subspaces? These subspaces appear everywhere in science and technology.